Let's break down a playbook that quietly changed how a lot of the best engineers worked this past year. Loop engineering, the Anthropic playbook for designing systems that prompt your agents. By the end, you'll understand how one person, fast asleep, can outship an entire team, and the single quiet decision that determines whether that makes them a sharper engineer or the helpless gatekeeper of a machine they can no longer read. For about 2 years, the whole game in AI was learning to talk to the model better, sharper prompts, cleaner context, a well-armed agent. This playbook makes a stranger claim. The real move is to stop talking to it at all. You get out of the chair, and you build a machine that sits down and prompts the agent for you, over and over, on a timer, while you're off doing literally anything else. They call it loop engineering. And here's the twist that makes it worth your next 20 minutes. Give the exact same loop to 2 different engineers, and 6 months later one of them is dramatically sharper, and the other has quietly become useless, unable to read the very code their loop keeps shipping. Same tool, opposite people. Let's figure out what actually separates them. Start with the world you already live in. You sit down, you prompt the agent, it does one thing, and then it stops and waits. It waits for you to read the result, decide what's next, and type the following instruction. Every single tick of that cycle has to come from a human, because you are the clock, and that's the quiet tragedy of it. The agent can generate at machine speed, but the whole system can only move as fast as its slowest part, which is you, one keystroke at a time. You aren't really directing the work anymore. You've become the bottleneck sitting in the middle of it. So how did we get here? Think of the last 2 years as a staircase, roughly 1 floor per year. The bottom floor is prompt engineering, getting the wording of a single request right. 1 floor up is context engineering, deciding what actually goes into the model's window, what to retrieve, what to summarize, what stale junk to clear out. Above that is harness engineering, arming a single run with the tools it can call, the actions it can take, and a clear definition of done. Each floor mines something bigger than the one below, from one sentence, to one window, to one whole run. And loop engineering is the 4th floor, the one that finally automates the part every floor below left untouched. The waiting for you. Here's the definition from Adi Osmani, the engineer who named it. Loop engineering is replacing yourself as the person who prompts the agent and designing the system that does it instead. Read that twice, because the entire weight of the idea sits on the words replacing yourself. You are no longer the engine that feeds the agent line by line. You become the person who designs the engine. And this didn't come out of a lab. In a single week of June 2026, 3 people, Peter Steinberger, Boris Cherny at Anthropic, and Osmani, independently reached for the same idea, because the tools had just crossed a threshold where running an agent on a timer stopped looking wasteful. The name showed up months after people were already doing it. And here's how the playbook puts it in one line. So what does that 4th floor actually add? 3 verbs, and they're the whole difference between a harness and a loop. First, it runs on a timer. It wakes up on a schedule with nobody pressing a button. Second, it spawns helpers. A single turn can split off subagents, one to draft a change, and another whose only job is to tear that change apart in review. And third, the crucial one, it feeds itself. Whatever the loop produces this round becomes its own input next round. Yesterday's findings get written to a file. This morning it reads that file and carries on. That memory, carried across runs, is exactly what makes it a loop, and not just the same task fired off 100 separate times. Now the single most important intuition in the whole playbook, because it's also what makes loops dangerous. Take one bug, an agent that misreads what a function returns. At the prompt layer, that's one wrong answer in one exchange. You catch it instantly and rewrite. At the harness layer, the agent acts on it once, but the run ends. The change sits right there in the diff, and you review it before anything ships. But at the loop layer, that misreading gets written into the state file, read back tomorrow morning as established fact, and built on, turn after turn. By the time anyone looks, the wrong assumption is load-bearing. The cost of a mistake scales with how many turns it survives before someone catches it, and a loop is, by construction, a machine for maximizing turns. Alright, what actually happens inside one turn of a loop? 5 moves, always the same 5. Discovery. The loop figures out what's even worth doing this round. Handoff. It passes that task to an agent to actually do. Verification. Something checks whether the result is any good. And this is the move that can say no. Persistence. It writes down what happened somewhere that survives. And scheduling. It decides to come back and do it all again, which is the move that turns a single run into an actual loop. Drop any one of these 5, and the loop either won't turn at all, or it spins in place accomplishing nothing. Let's watch all 5 inside a real one. Here's a real loop, the simplest kind. Osmani's own morning-triage. Overnight, nobody's awake. At 6 a.m., an automation fires on its own. That's scheduling. It runs a triage skill that reads yesterday's failing tests, the still open issues, and the recent commits, and decides which of them are actually worth acting on. That's discovery. And notice the loop finds its own work rather than being handed a list. For each finding worth doing, it opens an isolated work tree and hands it to an agent to draft a fix. Handoff. A second agent reviews that fix against the project's tests. Verification. Then it opens the pull request, updates the ticket, and writes progress into a state file so tomorrow picks up where today left off. Persistence. 5 moves, 1 turn, and you slept through all of it. Those 5 moves don't run on willpower. Each one needs a concrete part to stand on, and there are 6. Scheduling runs on automations. Handoff runs on worktrees. Gets built-in trick for giving each parallel agent its own directory, so 5 agents don't trample the same file. Discovery runs on skills. Project knowledge made permanent in a file, so the agent doesn't read-arrive what is this project every single morning. Osmani calls that save cost intent debt. Verification runs on subagents. The writer split from the judge. And persistence runs on memory, real state written to disk. And memory is not the same as context. Context is what the agent sees this round and forgets on refresh. Memory is what survives to tomorrow. The agent forgets. The repo does not. Now the hardest part of the entire playbook, and the one worth slowing down for, verification. Because the agent that just wrote the code is the single worst candidate to judge it. Ask an agent to grade its own output and it will praise it. Confidently. Even when a human can plainly see the work is mediocre. This isn't a smarts problem. It's grading your own homework. When the agent looks back at its code, it doesn't see the result fresh. It sees the whole chain of reasoning that convinced it to write the code that way in the first place. And inside a loop, that flaw compounds. If every "is this good enough" is answered by the thing that just did the work, each turn it nods at itself and drifts further and further from reality. The playbook states the finding plainly. So the obvious fix, just tell the agent to be harder on itself, barely works, and the reason is structural, not a matter of wording. You cannot ask an author to genuinely step outside its own perspective, but you can do something else entirely. Swap in a second agent, with completely different instructions, that looks at the code cold, carrying none of that self-persuasion. And here's the counterintuitive part the playbook leans on. Tuning an independent skeptic to be genuinely harsh turns out to be far more tractable than making the original writer critical of its own work. The idea is lifted straight from generative adversarial networks. One network builds, one network picks faults, ported to a generator that writes and an evaluator that reviews. But swapping in a second agent isn't enough on its own, because an evaluator that only reads the code is judging does this look right, not does this actually run. So the trick is to let the evaluator act. On front-end work, engineers wire it up to a real browser through a tool interface called MCP, so it can open the page, click the buttons, take a screenshot, and inspect what actually rendered, like a real QA engineer. That shifts the judgment from "this code looks fine" to "I clicked it, the page navigated, here's the proof." 2 more calibrations matter. Swap the underlying model too, because the same model with new instructions keeps its old blind spots, and tell the evaluator to assume the code is broken until proven otherwise. The default stance is doubt, not trust. And then you close the loop with a stop condition. In Claude Code, this is a built-in primitive. You hand an agent a condition, say, every test in the auth folder passes and the linter is clean, and it keeps running turns until that condition actually holds. The crucial detail, after each turn, whether the condition is met gets checked by a separate, fresh model, not the one doing the work. Completion is judged by an outsider. That's the maker-checker principle, and it isn't new. Banks have required that the person entering a large transfer and the person approving it be two different people for decades. A loop's ceiling is set by its generator, but its floor, what it will flatly refuse to ship, is set entirely by its evaluator. Quick breather. If a system that ships real code while you sleep, plus the discipline that keeps it from quietly wrecking you, is the kind of thing you want explained properly, do the free stuff that keeps this channel alive. Like, subscribe, and send it to the one friend who's already knee-deep in agents. Okay, loops in the wild. The fastest way to understand a working loop is to look at the 5 ways they break, because each failure is exactly one of the 5 moves skipped. Skip verification and you get the nodding loop. It approves its own work every round and quietly stacks up plausible-looking mistakes. That's the most common failure by far. Skip persistence and you get the amnesiac loop. It forgets what it did and redoes the same work tomorrow. Skip scheduling and you get the manual loop, which is really just a script you ran once and forgot to run again. Skip discovery and you get the blind loop, where you're still spending your morning deciding its work for it. And skip handoff and parallel agents collide in the same directory. 5 moves, 5 ways to fall. Now the loops people are actually running today, and they span a wild range of scale, but underneath, they share one skeleton. A trigger presses start, a set of constraints keeps it on the rails, and a human checkpoint sits at the very end. That's worth sitting with, because running while you sleep was never really about how strong the model is. It's about how solid that skeleton is. At the small end is Osmani's one-person morning triage we just walked through, one machine, one engineer, the grunt work done before breakfast. At the other end is something enormous. Let's go there. This is Stripe's Minions pipeline, described by their engineer Steve Koliski. More than 1,300 pull requests merged every single week, not one line written by a human hand. And here's the counterintuitive lesson. It is not built on some secret, stronger model. It's a fork of an open-source tool. Its reliability comes entirely from the quality of its constraints. Watch how it's wired. The trigger is trivially light. You just mention a bot in Slack. But before the model ever wakes up, a deterministic orchestrator assembles all the context, scanning links, pulling tickets, finding the relevant code, because letting the model gather its own context is the least controllable part. So that job is taken out of the model's hands entirely. Anything ordinary code can decide never gets handed to a probabilistic model. Where you draw that line is what decides whether the loop is reliable. The number, straight from the playbook. One practical thing trips almost everyone up. What does running while you sleep actually require? There are 2 flavors of scheduling, and they are not interchangeable. Local scheduling runs on your own machine. It can fire every minute, and it can see your local files. But the second you close the lid, it stops dead. Cloud scheduling runs on a machine that stays awake without you. That's true autonomy, but it can't see your laptop, and it usually can't run more often than once an hour. So the choice isn't a matter of taste. It's mechanical. Is the work glued to your machine, or can it leave? A mature loop often uses both, local for the tight inner checks, cloud for the overnight sweep. So loops are powerful. Here's the part nobody puts on the brochure. A loop that runs itself is also a loop that makes mistakes by itself. And the more cheerfully it runs, the more quietly it errs. For costs accrue in the background, and every one of them is silent while the loop is running. None of them ever sounds an alarm. They're called verification debt, comprehension rot, cognitive surrender, and token blowout. They sound like 4 separate problems, but by the end you'll see they're really one failure wearing 4 different faces. Let's take them one at a time. First, verification debt. Every pull request the loop opens and merges saves you time up front, but that saved time doesn't just vanish. It turns into unverified output, quietly waiting to be paid back. The danger lives exactly in the gap between the test's pass and the code is actually right. All the cases your tests don't happen to cover. Nothing looks wrong. It accumulates invisibly, run after run, until one shipping morning it all comes due at once, in production. And the only real guard against it is the thing we just spent so long on, an independent evaluator, a different agent from the one that did the work. The playbook is blunt about the first one. Second, comprehension rot. And this is the one that really gets people. The faster your loop ships code you didn't write, the wider the gap grows between what actually exists in your code base and what you actually understand. Reading code is just more boring than writing it, and the loop has taken all the writing. So the code base keeps growing while the map in your head quietly stalls out. It never sets off an alarm, right up until a bug burrows into some corner you have never once read. The guard is almost embarrassingly simple. Read a sample of the loop's output every day and force yourself to explain a few of the changes out loud. If you can't explain it, your map has fallen behind the code. Third, cognitive surrender. And this one isn't about time, it's about attitude. When a loop just works, round after round, it gets deeply tempting to stop having an opinion at all and simply take whatever it hands you. The more reliable it gets, the easier it becomes to quietly outsource your own judgment to it. And that's the trap, because the loop can execute brilliantly, but it genuinely cannot decide. It can't tell you which output is right, only which one looks reasonable. The guard is one hard line you keep for yourself. The loop is allowed to do the work, but it is never allowed to decide whether the work was any good. Fourth, token blowout. The only one of the four that hits your actual bill and the hardest to see coming. A loop hatches helpers, retries when it fails, and runs round after round after round. So a single stuck bug can spin idle all night, burning money and producing nothing but an unfamiliar invoice by morning. The guard here is to set hard caps before you ever let it run unattended. A per-run budget, a daily budget, a maximum retry count. Those numbers aren't really about saving money. They're circuit breakers that turn an open-ended, all-night risk into a bounded one. Now watch why these four are really one problem. Picture a loop that opens 20 pull requests overnight, every one with green tests. Looks like a triumph, until you notice 3 of them hide a subtle bug the tests never covered. With no independent evaluator, those 3 merge. That's verification debt. Because you merged all 20 without reading them, your mental model of the code base now lags by 20 changes. That's comprehension rot. Because it all went so smoothly, you stop reading tomorrow's batch entirely, cognitive surrender. And because it spawned helpers and retried all night, the bill came in triple, token blowout. Each one feeds the next. The less you verify, the less you understand. The less you understand, the more you surrender. The more you surrender, the longer it runs unwatched. One failure for faces. So how do you actually build your first one safely? The playbook's answer is, start almost embarrassingly small. Step 1, run a simple recurring task on a timer. Step 2, give it real discovery. Have it read your failing tests and open issues each morning and triage them. And put that logic in a reusable skill, not a wall of text buried in a schedule nobody will maintain. Step 3, add a state file so it remembers across days. Step 4, and this is the most critical and the most skipped, add the evaluator, that independent check that can say no. Step 5, and only now, add worktrees so agents can run in parallel without colliding. The rule of growth, add parallelism last, after you've proven the checks actually catch real mistakes. Which brings us right back to the 2 engineers from the start. The playbook's central claim is an economic one. Loops make generation, code, plans, fixes, nearly free, and that leaves exactly one thing scarce. Judgment. The loop can generate 100 options. It cannot tell you which one is actually right, only which one looks reasonable. And the gap between looks reasonable and is right is the entire reason an engineer still exists. So a loop doesn't devalue judgment. It strips away everything that wasn't judgment and leaves nothing but. And because it's a faithful multiplier, it amplifies whatever you bring. Bring understanding and it scales your understanding. Bring laziness and it scales your laziness. Same loop, opposite people, separated by 1 or 2 checkpoints you either kept or welded shut. The whole playbook comes down to this one image. Let's rebuild the whole thing from memory as one clean recipe. Start above the harness, on the 4th floor. You stop prompting the agent and instead design a system that prompts it for you. Every turn runs 5 moves. It discovers its own work, hands it off in isolation, verifies the result with a skeptic that can say no, persists what happened to disk, and schedules itself to come back around. Those moves stand on 6 parts: automations, worktrees, skills, connectors, subagents, and memory. The hardest move is verification, so you split the writer from the judge and let a fresh model decide when it's truly done. And you watch the 4 silent deaths, because a loop is, above all, a machine for maximizing the number of turns a mistake gets to survive. The one-line version: stop prompting the agent and design the system that prompts it instead. Do that, and generation becomes nearly free, while judgment becomes the only thing left that's scarce. Which means the whole job quietly shifts from doing the work to deciding every single morning whether the work the loop just did was actually right. What sticks with me is that a loop is a perfectly faithful multiplier. It doesn't care whether it's amplifying your understanding or your absence, it just multiplies whatever you feed it. Which makes me wonder about every so-called time saver quietly running in your life right now. Is it scaling your judgment or slowly replacing it? That's my read. Tell me yours. Until next time.